Zirconia, yeah, and hafnia, yeah. And these are also not very complicated or take very long in terms of computations. I should note, mind you, and I have it written on all these slides though, that this is very much a collaboration, right? These particular materials was done in collaboration with Boris Kiefer here in the audience at New Mexico State. The potassium ones were done in collaboration with Gerd Steinle-Neumann. Okay, so these were using the existing infrastructure, I guess. I mean, if we want to say it, of local clusters, and we actually got some very nice results and so forth. But again, feeding back between each other. I got this. This is what I think it means. Does this make sense? Or I predict that you should get this particular structure, as Artem has shown this morning. Does that structure exist, or is that at least consistent with the measurements where we may not necessarily know the structure? Hasn't been figured out yet. So, in summary, I guess these are the four things that I brought up. We can use the computations as an explanation. Why did this happen? Why in these experiments did this particular observation occur? Okay? We can use it to verify. Theory can verify experiment. Experiment can verify theory. Okay? Is the theory good enough? Does it at least, are we understanding everything? Are we at least being able to reproduce our measurements? Or is there something fundamentally wrong with the measurements between groups and so forth? Often we find that measurements don't agree. Look at any melting curve, and you get that. We can use it for prediction. Okay? What's going to happen? This is what's going to happen. Does it actually happen? And then, most importantly, especially as we are finding more exoplanets, more super Earths, and so forth, planets that have much higher pressure and temperature conditions than our own, we really then have to rely on theory at this point to be able to get us to those very difficult conditions to access experimentally. And so we want to make sure that we can at least believe them at the PT conditions that we can readily produce. And I think that's definitely mostly has been the case as of late. So that's it. That's the interface for computations experiment.
For the beta decay, what is the explanation for the difference between theory and experiment?
We don't have one. Now we could, one might ask. So why the factor of 3 to 5 off?
Is it possible to predict absolute rates or only the relative change of the rate?
So the formula that we're actually calculating here, what's plotted here is just this delta lambda. So all we're calculating is what that total electron density is, and comparing it to what at zero pressure. So it's a relative change.
Right.
Yeah.
Can you compute lambda itself, not delta lambda, but absolute lambda?
Not in this method. No, it's just it's a relative change. So, and that's actually important. So we there are a number of parameters that you can change in these codes. How large your muffin tin is and so forth. And what we find is, yes, if you change, say, the radius of your muffin tin, you do get the absolute values can be very different. But when you ratio them, they're essentially the same. So I think that was what made us feel like we were doing at least everything correct, or as well as we could given the tools available. Is it a temperature effect? I don't think so, because the temperature would actually go in the opposite direction.
Experiments were done at high temperature?
No, the experimental data is all at room temperature. So I mean, there's not a big difference between the 0K and the 300K, but you would actually expect zero. So higher temperature would actually make the difference smaller because you're pushing things away from the nucleus. So you might expect then that these curves should lie actually above. So that doesn't really work. Yeah, unsure.
I just curious, for experimentalists who also do computation, I assume you don't want to spend a lot of effort to maintain your own large cluster. So from your perspective, what is the best for this kind of a theory experiment interface? Is that, how does this work better? For example, you just find the collaborator, use their facility, or do you prefer to see some community infrastructure that will help you to do that when without really closely tied to the certain theory group?
Well, I certainly don't want my own cluster. So that wasn't one of your choices, but I wouldn't want I wouldn't want my own cluster because I don't want to have to deal with the maintenance and benchmarking and all that so forth. Right. So maybe that means that a larger community-based infrastructure. Now, I have to say though, if I had never run a calculation on my own prior and just say, okay, well now I want to run a calculation at some anonymous user facility, like applying to the synchrotron, but applying to the Supercomputing Institute here in Minnesota or wherever. I don't necessarily know that for me that it's such a great idea. I mean, I think you need to be working with someone who actually. I don't claim to know all the background and all the intricacies of these computations. So I'm a little afraid that if it becomes a black box, that you're going to lose information. So there needs to be more than just a black box where I say, okay, crunch that. I think there needs to be more understanding that could be be done in terms of tutorials or workshops or what have you. But I think as someone coming in brand new, just without any guidance, it could be maybe dangerous. But that's.
This is, I think you were touching on an important point because many experimentalists don't appreciate that. Like you who have experience.
There are a lot of things you can, yeah.
I just had a quick question. In some cases, it seems like having this sort of really intimate communication between the experimentalists and the modelers is very important. And I'm wondering actually whether you feel that is true here. I mean, I was thinking about your very nice results where you did these elastic property calculations and you compare them to PREM. You didn't need the PREM developers in the room with you to talk back and forth on a day-to-day basis. I've done some work on fuel cell stability, and I did need them in the room because I need to know exactly every experimental parameter.
But I called them.
Okay, so that would sort of be my question. To what extent do we need really, really intimate interactions, or can we do things where, you send an email once every few months of a structure you think you found, an X-ray pattern, and say, hey, can you match this? Which, of course, is much less detailed communication, but seems to be a way a number of exciting discoveries were made. I don't know if you had a feeling about that.
Yeah, well, I mean, just on a, I'm getting a really weird look from Boris right now, but I'm going to use an example. So on a particular project that we're working on now, I mean, this is via email and via phone calls. I mean, we're certainly not in the same room and hashing things out that way. Not saying, I mean, that would be nice, but it hasn't been necessary. And so we just ran some experiments last week at the synchrotron, and we got a result, and it looks really exciting. And so, so I emailed them and say, hey, we got this result. I think this actually might work. And so he's, checking to see if that's seems, I mean, so there's like this play, this back and forth.
Last one.
So you have done both experiment and theory, so do you find both equally interesting or?
Interesting is a horrible word to use. But when people say things are interesting, usually they're not. No, no. I think they each have their own. They each have their own thing to bring to the table. I mean, when I was running these, first calculations, still as a student, running them with Gerd, like, wow, I can see why people like to do calculations. I can run like 20 different jobs all at the same time and go to a movie and come back and it's done, or whatever. I mean, and so I saw the appeal to that, but of course it's not just that. I mean, that would be an oversimplification, and that would seem like it was easy, and I don't mean to suggest that. I think both can be interesting in terms of trying to push the envelope and trying to make the advances and not just trying to reproduce what has been done. So there are ways, but theory has come a long way, certainly in the 10 years. So
Thank you.
okay.